Good afternoon. Today we will do our first revision lesson as requested. We will discuss in the first one the Hooke's law, and this is part of the unit deformation of solids. And we're going to look at what is happening when we put a load on a spring. Some learning objectives: how a spring extends under increasing load, how do we plot a graph of load against extension, and some A-level practical skills. Okay, let's see, we have some equipment. Mass hangers, masses, retort stand, bars and clamp, ruler and graph paper. Okay, so how do we set up this experiment? Okay, well, we use the ruler to measure the original length, we hold the spring in a clamp, and we establish a reasonable range for the load. Now we always start with a load of 0. Okay, and when you're doing this experiment you might need about 9 to 10 readings within the range. Okay, conduct the experiment. So for example, you start with 0 grams, 50 grams, 100 grams, 150 grams, 200 grams, etc. Okay, don't mix up that. We need to know the extension. That means when we put a mass or a load on the spring, we find the extension by the current length minus the original length. Okay, and then we plot the load, which is in Newton, against the extension. Now we can also look what is going to happen with the behavior of a spring when we even add more masses to the spring, and to see how the spring is damaged. Okay, and what will happen if we overload the spring and we are unloading the spring again. Okay, it's interesting to see. Okay, and you plot everything in the load extension graph. Okay, now what are we going to use for our graph? We are going to find the gradient. What would be the gradient of this graph? Okay, so when we add a load to the spring is going to stretch, and Mr. Hooke, he has developed a law for that. Yeah, so this is very simple. It's a little bit of repetition, so we can look a little bit beyond. We also want to know what is the behavior of the spring when we put two springs in series, and how are the springs are going to behave when we put two springs parallel. Yeah, we're also going to look how do we find the energy that is stored in a stretched spring. Okay, Hooke's law. What did he see? He stated that the change in length produced by a force on a wire or spring is directly proportional to the force applied. Now, when we are talking about directly proportional and you're making a graph, and remember not to forget that directly proportional means that the graph starts at 0 and has a straight line up. In other words, you can say, for example, in this experiment, when you double the load, the extension is doubled. Okay, and let's have a small look at our applet load on the springs. Okay, let's look a little bit at the Hooke's law, the spring, when we add some masses. Okay, I'm going to. Okay, so keep in mind that you need to have a reference point, so we use the ruler. So our unstretched spring had a length of about 45 centimeters. If we found the extension, move the ruler up, and we see that our new value is about 55 centimeters, so the extension is 10 centimeters. Don't forget to put the units right. We can do it in meters or centimeters, but be very careful when you're going to find the gradient. Okay, we add some more. Let's see, can I add this like this? No, cannot. So I have to replace it. I have to take this off, and then we add 50 grams. And we see now we get a new value of about 60. What was it? 60? Well, anyway, the extension is now doubled. And let's add another spring, and then we see that the spring is stretched more. Okay, now you can do this at home. You can do the lab. You can change mass, add it. Okay, but anyway, let's continue. When we look at the Hooke's law, we see on the vertical axis we have the force, and on the horizontal we have the extension, and we use meters. And when you do your experiment and you have a nice spring, you must see a very nice straight line, and you can calculate the gradient. And what would be the gradient? That is the spring constant. Okay, this is just Hooke's law, and Hooke's law is only when there is no overstretching or damage to the spring. Okay, so we may say that the extension is directly related to the force of the loads. Yeah, we can use this proportionality, and then we can say that F equals K times delta L, wherein K is the spring constant. Yeah, and the spring constant defines how stiff a spring is. Yeah, so you could use different springs in the experiment and find the spring constant, and you can relate which one is more stiff and which one is less stiff. Okay, right, then we find the gradient, triangle as normally, and remember you will use this also in your practical paper 3. Okay, okay, let's look Hooke's law as a special case. Okay, remember, the independent variable is the variable with change, so that is the load. Independent variable is the quantity that we are measuring, and it depends on the independent. It depends a little bit on how you are looking at the experiment, whether you put the independent on the vertical or on the horizontal. Okay, so what we do indeed for Hooke's law, we put the force on the vertical axis and the extension on the horizontal axis. Okay, let's have a look and see what is the difference between the three lines. Well, what is happening at C? In the beginning it follows a nice straight line, and then we will see by adding a little bit more load, and it will stretch way more. That means the material is going to deform. Yeah, and we say it behaves in a ductile fashion. Yeah, that means the material stretches more with a small extra force. Okay, if we compare A with B, then because of the higher gradient, we can say that A is a stiffer spring than B and C. And it's pretty logic because it extends less with adding some loads. Okay. What is going to happen when we put two springs parallel? And look at this experiment. Now we put a weight, two springs parallel, so actually the load is going to be equally divided over the two springs. So what would you expect for the extension compared with one spring? Well, we can expect that the extension is actually half of that of one spring. Yeah? Don't have to look too much at the formulas, but we can say that the weight is supported by two Fp and Fq, and we find a different spring constant. Okay? 4 springs in parallel. Don't look too much at the formulas. You can use it, but it's very easy to reason. If you have two springs, you put them parallel, then the spring constant doubles. Yeah, because the extension is simply half of the original. Okay. So we may say that K is Kp plus Kq. Well, considering that the springs are equal, K is to K of the original. Okay? What is going to happen when springs are in series? Now, look at this example. We have a weight. Now, Q is going to stretch equally as P. So, when we consider P and Q as equal springs with the same spring constant or the same stiffness, then P would stretch like the same as the original, and we have 1, and Q is going to stretch like the same as the original, so we get actually a double extension. So the spring constant, what do you think was going to happen with the spring constant, is going to be halved. Okay, we can use this again using the formulas, and we see that the total extension is delta LP plus delta LQ. So WK, that is the total. We can find a relation. Yeah. So K is effective. We don't look at the formula, but you can just simply reason. As we get a double extension, yeah, with the same load compared to a normal one, we can get a gradient that's actually much lower, and the spring constant is then half. Okay. All right. How do we find the energy in a spring? Well, which formula do we have for a force to calculate the work done or the energy? That is F times x. Yeah, force times a distance. Okay. So when we look at the force or the load versus the change in length, we simply can find the energy in a spring of the area under the line. Yeah, and this is actually an elastic potential energy because work has done and the force moves through the distance. Okay. So the energy that is stored, and this is a triangle, is then half times F times delta L. Okay. Obviously, we can only use this when Hooke's law is obeyed. In summary, we have seen Hooke's law and how we can use it to establish the spring constant. We discussed variables and how accurately establish the spring constant experimentally, and we have seen how combinations of spring in parallel and series can act as a single spring, and how we can find the elastic potential energy in a stretched spring to the work done stretching a spring. Okay, that's it, first one. Next video we are going to discuss the Young's modulus and different behavior of stretching of different materials when we put a load on it. Okay.